Okay, welcome back once again. Quickly, let's look at simple harmonic motion. So what you need to understand here is that what is even simple harmonic motion? What are the terminologies associated with simple harmonic motion? That is, the terms that you need to really understand before you can even do one or two things with simple harmonic motion. Again, you need to know that, okay, what do we mean by a revolution? When is a revolution said to be complete? And let's go gradually. Let's start with the definition of a simple harmonic motion. So simple harmonic motion is the what? Periodic motion of a body. And a body is said to undergo simple harmonic motion if, firstly, its acceleration is always directed towards a fixed point. Now, for a body to undergo simple harmonic motion, the acceleration of that body must be directed towards a fixed point. 2, its acceleration is directly proportional to the distance from that point. Its acceleration is directly proportional to the distance from that point. Now, you know, when a body is undergoing simple harmonic motion, oscillations, you know, you are dealing with to and fro. But when you consider a body that moves in a circular path now, a body that goes round the circle, you can say, okay, the time taken for this body to complete one go around, which is known as revolution, okay, is also simple harmonic motion. The complete revolution of a body is known as simple harmonic motion. So here now, if you look at this now, for a body moving in a circular path, when a body is moving in a circular path, it has 3 characteristics. It has constant speed. The body has a constant speed, changing or variable velocity, and it also has centripetal acceleration. Now, when a body moves around a circular path like this, that makes it, when it goes round and get back to the starting point, we call that one revolution. So revolution simply means the time taken for a body to complete one circle or one go around. So if you look at it, this body goes round this circle, and if you bring that mathematically, sum of angle at a point when it goes around the circle, sum of angle at a point is 360 degrees, and that 360 degrees is equivalent to 2 pi in radians. So therefore, if we want to talk about the period now, period taken by this body to complete one oscillation, remember that period is what the time taken by a body to complete one circle, and one circle is one revolution. That is period now for this, which could be for this circular path T, we could call it the circumference of the circular path over the modulus of the speed, or what we call velocity. So the period now is, circumference of a cycle is 2 pi r over speed is modulus of v. We can also use this as what? Formula for period. And similarly, period now is what? Time taken over number of oscillation. This is one. While frequency, on the other hand, frequency is the number of complete oscillation made in 1 second. Frequency is the number of complete oscillation made per second. So remember, frequency now, frequency F is what? Number of oscillation made per second, and therefore frequency here is measured in circle per second, the unit, and 1 circle per second is known as 1 hertz. So therefore, circle per second is also equivalent to what? Hertz. While period here, it is measured in, the unit is seconds. So we are through with this. Then we look at amplitude of a body performing simple harmonic motion. Amplitude of a body performing simple harmonic motion is the motion of the object, displacement of the object from the central or equilibrium position. The displacement of the object from the central or equilibrium position is known as amplitude. And then we've talked about revolution and the circumference of a circle, which is known as the total distance round that circular path, and that is equivalent to 360 degrees, which is 2 pi radians, and that will give you circumference over speed. All right, so let's go to the next part, which is the relationship between linear speed, which is v, angular speed, which is omega, and amplitude, which could be your A or your radius. So now consider the motion of a body in a circular path. The motion of a body in a circular path So let's have a circle. Now this is circle. Now when the body moves in a circular path, we divide that into 4 equal parts. Now consider that this body moves in this circular path. It moves here. This is the central or the equilibrium position, and therefore if this body is displaced from the central equilibrium position, we talk about the amplitude of the body. So the displacement of this body from a central or equilibrium position gives what we call the amplitude. So this part is taken as amplitude, and this is your y or x, y axis. Then if you bring this down, this talk about the displacement of the body, x, then you have the angle at which the body moves in this circular path, this. So the body moving in this circular path will move with constant speed. Remember, that is one of the characteristics of a body moving in a circular path, and it will also move with angular velocity omega. And at this point, you are going to have it as a product of the angular speed and the amplitude that will give this. So if we look at this case carefully from trigonometry now, if we go through so quatre, we can have it here that if you follow this, theta is this. We can have it that, okay, anywhere this angle theta is facing is known as the opposite. So you have opposite, we don't need the value here. We are dealing with adjacent, which is x, and the hypotenuse a. So adjacent hypotenuse gives us k. So from this point we can have it that cos k is theta equals to adjacent is x and the hypotenuse is a. So therefore make x the subject of formula here. X equals to a cos theta. Call this equation star. But we can define angular velocity. Let's use this. Angular velocity or angular speed omega as what? Angle turned through by a body. Angle turned through by a body, which is the theta, over the time taken for that body to turn through that angle. So if omega is defined as angle turned through by a body over the time taken, so that means we can have angle turned through by a body, if you cross multiply it to be what? Omega with what? T. Call this equation star and star. If I put equation star star back to this equation star, put star star into star, we are going to have it that x equals to a cos theta becomes omega t. Keep that as equation 1. Now by way of definition, we can say linear speed or velocity, which is v, is what? Your distance which is x, over time, which is t. So here now we can have that velocity v is distance x over t. So from this point I can decide to make distance the subject of formula. Distance becomes velocity times time. Is that clear? Keep that as one of the equation, also call that equation 2. Next page. So we've got an equation 2. By way of definition also, we can say what? Angle turned through by a body. Angle turned through by a body, which is theta, is what? The distance over the radius of the circular path. If you go back to that first, the diagram, distance, this is the distance over this part now can be the radius of the circular path, where this from here to here represents radius of the circular path. So we can also say, okay, angle turned through by the body is the distance over the radius of the circular path. So here now we can have this as this, call that equation 3. So from there you can make what? Your distance, the subject of formula, distance is now theta with what? R. Sorry, theta with R. So that is theta with R. But note, your R is the same thing as what? Amplitude, right? Yeah, that which is the radius of the circle. The radius of the circle So if you have R to be equal to that, record that angular speed, which is omega, is what? Angle turned through by a body over what? The time taken. And therefore from this part we have the value for angle turned through by a body to be x over r in equation 3. So instead of theta here now, put that value of angle turned through by a body, equation 3, x over r, everything divided by what? Time. So what do we have next? This will give us x over r divided by t over 1, which will make it to be x over r times 1 over t. Now that means angular velocity here is now what? X over r times 1 over t. But if you arrange this carefully, if we make it x over t, x over t x over t then times 1 over r. You see, what we still have there is t times r and r times t. That is commutativity. They are commutative. So this will give x over t, which is distance over time, is same thing as what? Velocity, because velocity is distance over time multiplied by 1 over r. So therefore, if we cross multiply now, omega here will be v over r, because v times 1 will give you that, which shows that you can have your omega as if you make v the subject of formula, v equals to omega r. This shows the relationship between linear speed and angular speed. But remember, this also could be written as v equals to omega a, since radius and amplitude are the same. All right. So let's still proceed. Again, we want to look at derivation of linear acceleration. Derivation of linear acceleration of a body. So at this point, if you want to look at this now, we need to go through the differential method. So for this standard, for A-level standard, you go through the differential method. So we use differential equation here. So before we can do that, you have to recall that x is a cos theta, right? We got that from the first sketch here. X equals to a cos theta, which is our equation star. So we need that now, where your theta angle turn through is what? Omega t. So this makes this to be x equals to a cos theta, now becomes omega t. Now this x represents your distance and this t represents your time. So if we want to look for velocity now of a body, now we need to look for velocity now, which is your linear velocity. Velocity is what? It's going to be what? Dx over what? Dt. Differentiating x with respect to t. So if we differentiate this, at this point we can apply the function of a function for this. But note here now, what we are dealing with is x equals to a cos omega t. So if you bring that out, we want to differentiate now. Note x equals to a cos omega t. So what I need to do here is, what you have here is what I'm going to take as u. You are using function of a function, and every other thing that is left becomes your x, because you want to differentiate. So using function of a function, so I'll say u equals to omega t 1, then x is what is left. It becomes a cos, we've taken everything here to be what? U. So once this is out, we can now continue that. Okay, I need to look for the u with respect to the t. Remember, omega is a constant. When you differentiate that t, differentiating t gives you only omega, because t raised to power 1, when you differentiate, you know, it's going to return to 1. How? That is, you have y equals to a x n minus 1. So sorry, a n x minus 1. A is your power, which you have as the coefficient before t 1. X becomes t, then the power is still 1 minus 1. So you are left with 1 t raised to power 0, t raised to power 0, 1. So that makes this to be omega. Then at the same time, I will look for the x over the u. And what is the x du? You are differentiating cos u, cosine of u. When you differentiate cosine, it gives you negative sign. So therefore, all I have here is just to say the x du is minus a sine u. Now, two values has been given already, du dt, the x du. So if we need the velocity now, which is the x dt, so we can just come here and say velocity. Don't let us make it look difficult now. Velocity is just multiply these two stuff together, du over the t multiplied by the x over the u. So that means the x over the t, which is our velocity, the x over the t now is, what is the u over? That is omega multiplied by minus a sine u. Are you there? Okay. So dx over dt becomes minus a, bring this omega, then sine u. So but u is what from this part? U is omega t. So put that back, omega t. So here anywhere you see u, replace it with omega t. So that means the velocity, which is the s over the t, is minus a omega sine omega t. But actually the question says we should derive the acceleration of a linear acceleration of a body. So at this point again, we still need to proceed again. We'll now differentiate this velocity. Remember the last point here, v is minus a omega sine omega t. Again, we'll differentiate this again by taking this part we'll take this part again to be u. So if you make that u again, you have u to be omega t. Then what is left is v. We are looking for dv dt at this time. So v now is now minus a omega sine everything here, sine everything becomes u. Okay, so now at this point you need the u dt again, differentiating this. When you differentiate that, that gives you omega. Then we need dv du again. When you differentiate sine, it gives you cosine. So therefore you are left with minus a omega cos, that becomes cosine now, cosine cos u. So at this point we need dv over dt. Remember, dv over dt is that word for acceleration, change in velocity over time. Dv over dt now becomes du over dt multiplied by dv over du. So put in the value a, which is our dv dt, will now be du dt is omega multiplied by dv dt minus a omega cosine u. So if you bring this here now, that means the a becomes omega is true there, omega squared dot, there's still minus a cosine of u now becomes what? U is omega t. So acceleration here now becomes, bring the a forward, minus a cos omega t, everything is still multiplied by what? Omega squared. Now this a cos omega t, but x is a cosine omega t. When we started the derivation, x equals to a cos omega t. Look at it here. So anywhere we see a cos omega t now, we'll quickly replace that with x. So therefore a now is a cos omega t, means we are left with minus, and what we have here is omega squared. A cos omega t becomes x. This is the expression for the linear acceleration of a body, or you can also write it as a is minus omega square a, where this x is still the same thing as the amplitude. Alright, where a is your linear acceleration, this small letter a, small a, is linear acceleration, this is amplitude, and this is the angular speed. Okay, let's quickly move to the next one. Angular acceleration. Angular acceleration, which is alpha. The angular acceleration of a body is the time rate of change of its angular velocity. Time rate of change of its angular velocity, and it is expressed in radians per second squared. So mathematically now, angular velocity is what? Change. So angular acceleration is change in angular velocity which is omega over time required for the change. Time required for the change. So here now, this is similar to when you talk about acceleration. You know, when you say acceleration now, acceleration is what? Change in velocity, where you have final velocity minus initial velocity over time. Same way you can deal with this angular velocity, same way, where you have the final angular velocity, call that angular velocity with t, then minus the initial angular velocity o naught, over time, which is t. But from the first relationship we added that v, but v is what? Omega r. So from here now we can make omega the subject of formula, which is angular velocity. That shows that what? Omega will be v over r. So anywhere we see omega here, we can replace that with v over r. So that makes angular acceleration to be omega t, which is vt final velocity over r minus initial velocity over r, all to be divided by what? T. If you look at this numerator, if we take the LCM of the numerator, you are going to have r equals to vt minus v naught, all divided by what? T. And if you look at the numerator, this is 1 over r. If you bring that out, 1 over r, you'll be left with vt minus v naught, all over what? Over t. But vt minus v naught over t is still same statement as this, change in velocity over time. That becomes your linear acceleration. So therefore you can say that angular acceleration alpha now becomes 1 over r dot this vt minus v naught over t becomes a, which is linear acceleration. So if you cross multiply, this will be a over r, multiplying this and this. That means linear acceleration is angular acceleration multiplied by the radius or amplitude, and that is also another expression for angular acceleration. So the angular acceleration here is alpha. So if you are asked to calculate angular acceleration, just make angular acceleration the subject of formula, which is a over r. Let's proceed. But remember that we said omega is angle turned through by a body over the time taken, right? Now this angle turned through simply means the total angle turned through by that body, the circumference of a circle or a circular path, which is time taken for that body to complete one revolution, which is 360 degrees, over the total time taken for that body to complete one revolution, which is known as period. Now 360 degrees, it's known as 2 pi in radian over t. So that means omega now is equivalent to 2 pi over t, which shows that t itself could be 2 pi over omega. Take note of this. But period is 1 over frequency, and frequency itself is 1 over period. So anywhere we see t here in this part, I can replace that with 1 over f. So that gives me omega equals to 2 pi divided by 1 over f, and that will be 2 pi times f over 1. If you do that, that shows that omega, which is this, is 2 pi f, and that's another formula. Okay, so let's proceed to the last aspect for now, which is velocity at any instant of time. Velocity at any instant for a simple harmonic motion. Velocity. Okay, consider the sketch above. You have this again for velocity at any instant for a body performing simple harmonic motion. This part is the y, which is the maximum displacement of the body. This is the amplitude. This is angle theta, and this place is also theta because alternate angles are equal. If you follow trigonometric ratio now, you look at this. This is opposite where the angle is facing over the longest part here, which is hypotenuse. Opposite over hypotenuse gives us sine of the angle theta, which is y over r, which is from this figure. So if you cross multiply, y is going to be r sine theta. theta, but theta, which is angle turned through by a body, is omega t, which gives this. But this part now, you have two things that you need to consider here. You have distance and you have time. So I can differentiate distance with respect to time, and when we do that, that becomes what? Velocity. Velocity here becomes the y over what? The t. So we'll do the same thing that we did for acceleration of a body performing simple harmonic motion. Take this part as u, and every other thing becomes y. So u here is omega t, and y becomes r sine u. So here now we need what? The y du. So firstly we need the u dt, the u dt, which is going to be omega, and at the same time we need the y du, the y du, which means when you differentiate sine, you are going to get what? Cosine, positive. When you differentiate sine, cosine, positive, that gives you r cos u. So put that back, which is, we need the velocity now, velocity, which is the y over the t, that represents velocity, and that gives r omega cos u. I multiply this with this, and that gives v now, velocity, to be r omega cos u. Here is omega t, so that gives omega t. Call this equation 1. So similarly, from this sketch now, from this sketch we have it that from the sketch we have it that sine theta is y over r. Sine theta is y over r. So if you recall that from trigonometric identity, recall that sine square theta plus cos square theta, everything is one, right? But from this sketch now, we can make cos theta the subject of formula from this trigonometric identity. So you have cos square theta equals to 1, then bring the other one here, minus sine square theta. Cos square theta means cos theta with squared, which is 1 minus sine square theta. So that means cos theta will be square root of 1 minus sine square theta. Good. Now you will now say, but we just concluded that sine theta itself is y over what? R. So if we need sine square theta, what happens to that? We square it. That means sine square theta becomes the square of y over the square of r. Put this back to this equation. Anywhere you see sine square theta, replace it with y over y square over r. So that gives cos theta becomes 1 minus y squared over r squared. So this, take the LCM. LCM here is r squared. R squared divided by 1, that is 1 times r squared. So you are left with r squared minus y squared. So cos theta could be, you can have this as split the square root from side. You have r squared minus y squared, put plus or minus here, over root of the other part, which is r squared. Square here will cancel this square root, but that is not applicable to subtraction, because from side m minus n is not equals to root m minus n is not equals to root m minus root n. So it's not. So we can't do that here. So this actually becomes plus or minus square root of r squared minus y squared over r. Now, so that is going to give so that becomes cos theta equals to, now you have, that was where we saw plus or minus r squared minus y squared over r. Now bring this, this is looking like 1 over r now, so you have cos theta equals to 1 over r, which is 1 over this, with plus or minus root r squared over y squared. Keep this as equation star star. Now put this equation star star back to our equation 1. What is that equation 1? Where you added that here, where you have it at v r omega cos v equals to r omega cos omega t. So put that equation back to this part. So put star star into equation 1. And what is equation 1? V equals to r omega cos omega t. So cos omega t, which is still same thing as v, equals to r omega cos, omega t here is still same thing as what? Theta. So which is cos theta. So this cos theta now, the value of this cos theta will now be substituted here. So you have v equals to r omega dot cos theta 1 over r plus or minus square root of r squared minus y squared. R here, cancel this r, so we are left with v equals to omega plus or minus root of r squared minus y squared. And this is known as velocity at any instant of a body performing simple harmonic motion. But in some cases, this could also be represented as your r here could stand for the radius or the amplitude a, while your y here, the distance, could be x. So this formula could still be v equals to omega plus or minus here. Now r is a squared minus y is x squared. It is still same as velocity at any instance of a body performing simple harmonic motion.